Welcome to class meeting number 9 of the Introduction to Optimization. So, as always, let's start with announcements. So, the homework number 2 is due on March 22nd. Is it Monday? Yeah. Monday, and okay, Wednesday. We will have some additional problems to homework number 2. They will be announced during today's meeting. You need to actually just copy and paste the proof in the textbook. The reason why I ask you to do that is, anyway, you need to follow the proof at least once. Okay, it seems that something's stuck here. Okay. And about the exam number 1, do we have agreement, consensus? Not yet? Okay, it will be soon announced. Okay, so we will take the first exam during this March, okay, during this month. Okay, review. So, where were we last time? We were covering chapter 7, is it correct? Yeah. What was the title? One-dimensional search methods, right? So the general iterative algorithm we are going to develop almost throughout this course looks like this. We start from our initial guess, and after the first iteration, we have another vector. By the way, all these x sub k's are in the constraint set. Okay? So we update our feasible solution at each iteration. Okay. And whenever we update, we can view this update this way, like the k plus first estimate of our optimal solution, or k plus first candidate solution is something like this. Okay. Anyway, you can subtract them because we assume this omega is a subset of Rn, which is a metric space with Euclidean norm metric, right? So we subtract, and this becomes kind of difference between current estimate and next estimate. Now let's kind of decompose this into 2. So we view this one as what? Some step size times such direction. You can do always, right? Because anyway, the difference between 2 estimates is a vector, and you can arbitrarily choose a scalar and leave the other thing in this vector. Okay? So you can view our iterative algorithm to solve an optimization problem always looks like this. Okay? Given that, what were our topic? Maybe our objective function itself is a one-dimensional function. Means it's a real-valued function of a single parameter. In that case, these are scalars, right? So there is no direction actually. You can just drop this and you choose some scalar. Okay. In that sense, we had one-dimensional search problem, or even if our objective function is a function from Rn into R, if we fix, for example, at each iteration, if we fix our search direction in some way, then what is left? Choosing the step size is left. Now this is a scalar, so in that sense it is reduced to 1D search problem. So anyway, this one-dimensional search may be important. That's why we learned it. And I somehow gave you a little bit big picture of what we learned last time. The topics were like this. We learned first the bisection method. Actually, a bisection method, because there are many bisection methods. Okay? For example, if you want to find a natural number among 1 to 50 using 20 questions, a bisection method will be kind of optimal in reducing the uncertainty interval at each time. Okay. Now, what did we have? We have the golden section method or algorithm. And what did I mention? I also mentioned the Fibonacci method, Fibonacci search method. Okay. And what else? What else did I mention? Newton's method. Okay. And the Newton's method for one-dimensional search, and it has an alias, a nickname. What? Newton's method, the Newton's method of tangents. Why suddenly we have Newton's method of tangents? Because if we substitute f prime with g, then a geometrical interpretation of this Newton's method was what? Related to tangents of this function g. Okay? And similar algorithm we had, what was that? The Newton's methods, if you want, method of secants. But it is simply called the secant method. Okay, so we learned these 5 methods where I didn't much explain about this Fibonacci search method. Okay. Now, how do we classify this? First, there are many ways. First, what if we cannot use the first order derivative of the objective function? Which is applicable? Bisection? No, because in order to use bisection, we need the first order derivative. But actually, before talking about that, for these 3, we assumed what? We assumed the unimodality of the objective function on a closed interval. So, what is important is that you have to know the limitation of the algorithms. Okay? So, the key limitation of these 3 were what? First, the f is unimodal on a0, b0, the closed interval. By the way, this closed interval a0 to b0 is our constraint set. Okay? So the first 3 algorithms are applicable to that case. Okay? And what is the difference? This bisection method requires f prime of x. Okay? The first order derivative. What about the golden section method? You didn't need. Okay, that's why from the bisection method, when you move to bisection to goal section, you need to evaluate 2 points of the function. Okay, but actually goal section method evaluate one new function at one new point by tactically, cleverly reusing previous point. So actually, complexity is not that different. Okay? And what was the difference between these two? Okay, commonality is that it only uses f, right? What is the difference? What is the difference? Okay, whenever you iterate the ratio of the previous current uncertainty interval to next uncertainty interval is fixed here as a golden ratio, 0.618, right? But here it's varying, okay? And that ratio is a function, actually 1 minus ratio of 2 consecutive Fibonacci numbers. Okay. So what the difference is that fixed ratio in reduction, and here varying ratio in reduction. Okay, so got it? So which one looks better? Actually, this is faster, but there is a problem. Okay, if you pre-specify number of iterations, then this Fibonacci search gives you the minimum length of the uncertainty interval at the after the nth iteration. However, this golden section method does not require for you to pre-specify number of iterations. You can just iterate until you are satisfied. Okay, got it? So in that sense, they are different. But if you pre-specify the number of iterations, this is better. The textbook proves that this is optimal in recycling the previous point and reducing the uncertainty interval. Got it? Okay, so you have to know the commonalities and the differences. Here, the Newton's method of tangents and Newton's method of secants. Okay, how they differ? First, anyway, they need f prime. So let me say this. Okay. Anyway, f is continuous. Okay. So f is continuous. F is C1. Okay. Actually, let me see. F is C1. Okay. So anyway, we use first order derivative. In that sense, they have the commonality. But what about Newton's method of tangents? Actually, it utilizes double prime. Okay. So here, this is used. Okay. Here, only f and f prime are used. So actually, this secant, what is a secant? Given a curve, we call a line that intersects at 2 points, okay, or more. We call the line a secant line. Okay. What is a tangent? Tangent may intersect more, but it touches the curve, right? So in that sense, they are different. So this tangent is kind of replaced by a secant line. Okay. That's why we could remove the use of this one in the secant method. Okay. As I emphasized, these are to find the local minimizer, but it may fail, okay? Because we do not have much assumption. And this name, tangents and secants, are vivid when you transform the problem not to minimize the function f, but to find the zero of f prime, that is called g. Okay, got it? So this is the big picture. Okay, and here goes our preview of chapter, is it 9? Chapter 8, right? So, what is the title of chapter 9, I believe. No, 8 is correct, right? Chapter 8. So, what is the title of chapter 8? Gradient methods. Okay. So, I also want to, at this point, remind of myself being at your position. Okay. When my professor started to teach chapter 8, I had a lot of confusion. Okay. Because I just could not focus. It's like, is this for some quadratics? Is this result general? Okay. In that sense, I had a lot of pain. And I compared my note with your note, and your fourth edition and third edition, found that professor actually reorganized the sections a little bit to reduce the confusion. But still, I believe you may have a lot of confusion when you read this, especially lecture note. Okay? So I'm going to put a Venn diagram that I hope may greatly help you. So here is a Venn diagram. So suppose this big set, superset, universal set, contains all iterative algorithms. Okay? Set of all iterative algorithms. What does that mean? This algorithm is somehow find the next estimate from the previous estimate of the optimal solution by, it has a structure, by the step size at the kth iteration times the search direction at the kth iteration. Okay? This is what I just told you, right? In Euclidean n space, so iterative algorithms for mean f of x subject to x in omega in Rn, right? So any iterative algorithm can be put in this form, right? So this is very general. Now, our algorithm depends on how we choose the kth step size and how we choose the kth search direction when we update this kth estimate. Am I right? This should be clear. Otherwise, you will have a lot of pain. So, first, let's focus on this one, the step size. There may be many ways to classify algorithms depending on how alpha k is chosen, but the simplest one is this. Is alpha sub k fixed for all k, or are we going to vary this step size, right? So in the sense, first, so let me pick this one. So first, we have variable step size iterative algorithms. Okay? So we have a subset. So if we have an algorithm here, it has in general variable step size. So alpha k may change. Okay? If an algorithm is here, then it has some fixed number. Okay? Somehow calculated. Now, second term, second factor. There are many different ways of choosing this such direction. And in this chapter of chapter 8, by the way, what was the title? Gradient method. So this is chosen as what? The negative gradient. Okay, because we assume that if this is named as the such direction, alpha is positive. Okay, we go that direction, not the opposite way. So in gradient, in this chapter, we choose d sub k as negative gradient. Okay, so we may have another subset and gradient methods. What does that mean? D sub k is negative gradient evaluated at the current estimate. Got it? By the way, for convenience, as we did in the Newton's methods of tangents and Newton's method of secants, we want to call the first order derivative as g. Okay, so I'm going to end the textbook use g, but here be careful. This is g. Okay, so minus g k. Okay, so this is definition. Okay, we are actually notation we are going to use. Got it? So this is gradient methods or gradient method. Okay. Now here one more thing is left. That's why I left this space. Is this some algorithms may have very good property, and I've already told you. Okay. This is somewhat strange, but it's like this. Before, okay, for all k where gradient is not zero, for all k such that gradient, so gk, k is not zero vector. Okay. So until it reaches to the local minimizer, at every step you reduce the function value, objective function. This property is called descent property. And some algorithms, so using this definition, we can also divide algorithms, iterative algorithms, into two. One, those having descent property. The other, those do not have descent property, right? So let me put one more circle here. So descent algorithms. Got it? This should be clear. Okay. Of course, textbook does not have it. As I told you, I really love simplification and visualization. Okay. Actually, last Sunday, my wife asked me to explain some solution of my third son's some exercise problem. Okay. And it was so-called a problem for Olympiad level. And it was quite confusing. So what I did was first simplify the problem. And it seems that that simplification does not help me. So what I did was what? Visualization. Okay. And I could solve it. Okay. I was also amazed. This simplification and visualization really works. Okay. So never forget. This is a way to understand today's lecture. Okay. Given that, we especially focus on two things. Let me mark it as X and let me mark it as plus. Okay. These two algorithms are very important. Okay. Today. Okay. The first one is what? it's a gradient method and it has variable step size and it also has a descent property. And this is actually called the steepest descent algorithm. Let me little bit move this one. So this X is steepest descent algorithm or method. But be careful, okay? It only has two qualifying adjectives, but it is a gradient algorithm, okay? It utilizes the negative gradient as its search direction at every iteration. Okay? So if I were the author, I would say steepest descent gradient algorithm. But anyway, the chapter is entirely on gradient methods, so the qualifier gradient is dropped, but anyway. So three things intersected. Naturally, when this algorithm is applied, it has variable step size. That's why I put it here. Okay? It may have fixed step size in a very special case and with very special initial point. But in general, it's a variable step size. You will see why. And second one is here. And it's a just fixed step size gradient method. See that this is not in the variable step size set, which means it has fixed step size. And it still utilizes gradient method. See that this is fixed with some number alpha, and this is negative gradient at each k. Okay, so this is varying, but anyway gradient. Done. Okay. The problem is that this may not have descent property. Got it? So we are going to examine these two. A very interesting property we will see. Another thing, another preview is that we will learn some results applicable to general f that is once continuously differentiable and only a quadratic function f of x equals half x transpose q. Let me see. Yeah, it's okay. Minus they used. Okay, b transpose x plus c with positive definite symmetric matrix Q. Okay? So some of the results are only applicable to this. So you must be very careful, otherwise you will suffer a lot of confusion, as I did 21 years ago. Okay? I don't want you to have that suffering. Okay, so let's have that in mind and take a look at our lecture note. Okay. So as I told you, this entire chapter 8 is on gradient method. What does that mean? Such direction is the negative gradient at each xk. Got it? So this is what I told you, and this gradient will be called g. So as you see, this is d, right? So alpha is the step size, that is a positive number. And here, it first justifies why this gradient method is good. Okay? You will see today two things. pros and cons of a gradient method. So first pro, then con. Okay. What is pro? Why we advocate using a gradient method? It shows that we have a descent property if we cleverly choose our step size. Got it? Since our search direction is fixed now, not fixed, it's restricted to a negative gradient, we are only left to choose a step size. But one good news here in this proposition is that there exists a step size that guarantees descent property, always. Okay. So if I were you, in your PDF note, okay, I will have a bracket, big bracket. Okay, so it's your page 1, okay, 1/11. I will somehow bracket like this from this proposition line. Okay, so from here to this point. Okay. See that these are all same level itemizing bullet, but up to this one. Okay, so from here to here, okay, it's about this proposition. Okay, and from here it talks about different thing. Okay, it's very important. Otherwise, you will soon get confused. Okay. So that proposition and proof just shows that why a gradient method is good. And this is quite natural because consider that. Suppose you have not yet reached at a local minimizer. Then what happens? That direction is non-zero vector, right? Now, according to the calculus, if function is one time continuously differentiable, you can move if there is a very small number, or it could be large. If you move that amount times negative gradient, your function reduces. This can be proved using, again, little o notation, right? So I'm not going to repeat it. It's too obvious, okay? And here, okay, the authors emphasize that still we have freedom. Okay? So what does this mean? A gradient method is not unique. Okay? Even though you choose to use our negative gradient as our search direction, still we may have many algorithms. Okay? Now, even if we restrict it to a descent algorithm, okay? If we just ignore this descent property, we may have more algorithms. Okay? Now, from here, from here to here. Okay. So actually, these bullets must be a little bit lower layer bullets. So several possible choices. One, you choose alpha k generally very large. What will happen? Sometimes you may not have descent property, right? You may increase your function by choosing at some step, after some iterations, right? And also, you may, for example, function looks like this, and you start it here, and step size is too large, then you may just overshoot every time. If alpha's subcase are chosen generally very small, what will happen? It will move very slowly. Okay. So anyway, there are many ways, or we can choose some fixed number. And again, depending on how to choose that number, you may have trouble. Okay. But anyway. What is good is this. Okay? There is a very simple way to have a kind of locally best algorithm. See this. Okay, this is greedy because this is what a kind of you do local optimization. Okay, greedy means local. Okay, so at each iteration, you choose your step size alpha sub k that minimizes this function value. So at the case estimate, case feasible solution, what you do is that you find the negative gradient direction. And you find step size that gives you the minimum of it. So you move to that. Okay. This is optimal at the kth iteration, right? But we don't know whether it is the best way or not. But anyway, so this is called the steepest descent gradient algorithm. Okay, as I marked as X, that lies in the intersection of these three subsets. What? Variable, gradient, and descent. Right? So let's examine the properties of this steepest descent algorithm. So from here, the proposition, this third Bewley to the first Bewley of page 3. Okay, you have one proposition and its proof. Okay, so again, if I were you, I'll put a kind of bracket starting from that Bewley and to the first Bewley on page 3. Okay, now let me explain what is going on here. Okay, the key is that this is general case. It looks like a quadratic function, but it is not necessarily quadratic. So let me give you a more clear one. Okay. So this is proposition 8.1 related thing. So this is a property of the steepest descent gradient algorithm for general function f that is continuously differentiable. Okay, so this is very general. Okay, and you will see other results that are mostly applicable to quadratic functions only. Okay, so this is general. Remember this. Okay, and let's start from, and for simplicity, let's assume f is from R2 to R. Okay, so we can visualize the level sets in this plane, right? So first, suppose you start from a point that is x0. And suppose this is the negative gradient direction. Okay, so that is g of 0. Okay, got it? Now, what is our interesting property? What is our interesting property? Probably you remember from our review, one of our review chapters, that given a continuously differentiable function, the gradient vector and of course the negative gradient vector, because that is proportional. If it is not a zero vector, it is what? Perpendicular, orthogonal to the tangent vector, which means that touches the level set. Okay. So here, suppose that you have f of x0 equals c0. Then the level set will be orthogonal to this g0. Am I right? You can prove this, or you can find the proof in the text. Okay. Now, what is the steepest descent? You move this direction, and reaches local minimum. Okay, suppose this point is local minimum. Then that point becomes x1. Am I right? Now, you evaluate the function at here. So, let's set this as C1. Now, draw the level set of this function f at the level C1. Then you again knows that what? There should be a level set, right? Am I right? But question, okay, is this level set has its tangent parallel to this vector? It seems, because otherwise, right? Otherwise, you can move further to reduce. Okay, so this is what we are going to say. Okay, see, now consider vector, the vector from here to here, and the vector from here to some x2. Okay, it seems they are orthogonal. Right? Actually, that is this property to be shown in this proposition. Got it? So here you have x2, and again some level set. Let me draw a different level set. Let me see, just a second. So you move to here and then this direction. Got it? So this is x3. So the important property to be shown here is this. The vector xk plus 1 minus xk. What is this, by the way? Alpha k dk, right? And alpha k gk. Why? Because in gradient methods, this is negative gradient and this is negative gradient. Got it? Now, what is the next one? 2 plus 1. Alpha k plus 1 dk plus 1 is minus alpha k plus 1 gk plus 1. Okay. And our claim is that these two vectors are orthogonal, as you can see here. Am I right? What does that mean? These two vectors are orthogonal. What does that mean? We assume we haven't yet arrived at a local minimizer, so these alphas are not zero. Means that these gradients are orthogonal. So actually, this is orthogonal if and only if gradient of f at k and gradient of f at xk plus 1, when they are inner products, it is 0. Okay? So we want to show this. And the proof is not that difficult and it's followable. You just show this using first one necessary condition. Okay? Not difficult. You can do it. Okay? What I want to emphasize is this. Okay? We just have had a general formula. Okay? This is general, as I emphasized. This is maybe the only general result we learned today. Okay? For general, continuously differentiable objective function, our steepest descent gradient algorithm has a very interesting property. What? Such direction vectors are orthogonal. What does that mean? Suppose we want to reach here. This is very important. And you may say that the best is moving from here to there at one iteration. Am I right? The problem is that it moves kind of in zigzag form. Okay? It's like I want to go there, but unfortunately my original direction was not here. So what I do is that I move this way. Okay? At every iteration I do the clockwise 90 degree or something like that. Okay? So is this good or bad? This is little bit bad. Okay? When? Depending on the shape of the function, this may require a lot of iterations to reach the local minimum. So this actually proposition shows the cone, okay, the weakness of the gradient method. That's why actually we have other algorithms that use non-gradient method, which means that our such direction is not the gradient vector, but something other. Got it? So this is a proof of cone. Okay. So we are done here. Okay. So this is to show a cone of steepest descent gradient algorithm. Got it? So let me little bit summarize for pros and cons. What was the pros of a general gradient method? We may have a descent property. And if we choose steepest descent, this descent property is guaranteed. That's good. Okay? We can find a very good algorithm, but then even the algorithm has some problem. Steepest descent gradient may have a very slow convergence. Okay? And this figure even shows that it may iterate forever, okay, to reach this x star. Okay. So we need next lines, okay, from here to here. Okay. So we need to stop anyway. Okay. We need to stop at some point. We cannot iterate in forever. So there are so-called stopping criteria, and there are many different stopping criteria. So we have, among them, we have these 4 stopping criteria. Okay. Of course, there are many others. Okay. And here, what is this? If at the kth iteration, our direction, such direction vector is less than epsilon, its magnitude. Okay. So it says that the gradient value is very small. It's almost 0. What does that mean? You already possibly very close to a local minima. Okay. It may not be true, but it is highly likely. What is this? You move, but from k minus 1 to k, you just move little bit. Okay. And you may say that, they are good enough. Okay. I may use both of them, but there is a problem. Suppose you just scale your function. Okay. There are 2 ways to scale your function. First, you scale this x. Okay. You changed it from the unit as meters to millimeters. There should be no problem, but actually if you put it in the MATLAB, it's a totally different problem, right? MATLAB will recognize, for example, function moves, changes very, very slowly, and it automatically stops if you just do not change this epsilon. Second, you may scale your function value. For example, this objective function has unit liter. Now you change it to milliliter. What will happen? The same thing, right? So, unlike these two, of course there should be many others. These 2 stopping criteria has some way to normalize this. See that? This function, even though this is first order derivative, what you do is that you normalize this gradient using gradient. So even if you scale this function, that value will not change now, right? Got it? And you may say that, wait a minute, why this is 0? I may use k minus 1. You are right, you are right. You may use, at the current gradient magnitude of the direction vector, you may divide it by the just previous one. It's your choice. There should be others, like x of k divided by norm of gradient of x minus k minus 2. No problem, right? This is just one of those normalization method. Now, for this one, you want to normalize this distance-related one. Right? You can normalize, for example, with the k minus 1 vectors, points, norm, or case, or if you want at the zero scales. Okay? There could be other normalization methods. Okay? Anyway, these are typical stopping criteria. You may use both of them. Anyway, by doing this, these are focusing on absolute kind of value compared to this relative value, normalized one. Okay, so the authors say that the last two are usually preferable because they are scale-free, as I just told you. Scale in such space, scale in the function value. Got it? Now, from here, we start section, I believe, 8.3. Okay. So from here, we analyze two algorithms, basically. But we could analyze some more. But anyway, mostly two algorithms. First one is, again, the steepest descent. Okay? That is what? That lies in the intersection of these three subsets. Variable, step size, and what? Gradient, and what? Descent. Okay. And next one is still a gradient method. So anyway, it should be inside the second one. But now it has a fixed step size. Okay. So we mostly analyze this performance of these two two gradient methods. Okay. The problem is that how can we analyze the performance of algorithm? We just arbitrarily choose an optimization problem, arbitrarily choose an objective function? No. In that case, the performance may vary a lot. So, as you remember, the reason why a quadratic function is very important in this course is that we use quadratic functions to test the algorithm's behavior and property. Got it? So, from this point, many of the results are applicable actually only to quadratic objective functions. Okay? So let me repeat. That zigzag property is for what? Is for steepest descent. For applied to general continuously differentiable objective. But from now, most of the results are applied to quadratic functions. That is very important. By the way, you read these things. Okay? Yeah. Okay, so, as I told you, a quadratic function is very important. But usually we use plus here, but anyway, in this book, we use minus. So that the gradient, the first derivative set to 0 gives us very nice result. What is that? If we calculate the gradient, then this becomes qx minus b. So what is our location of the actually global minimizer? Q inverse b. Okay, not minus Q inverse b, plus Q inverse b. That's why we have negative sign here. Got it? And another thing is that actually we don't work with this. We add a scalar value so that our manipulation is much easier. Our proofs are much simpler. The trick is like this. Suppose you want to add some constant such that this one becomes a complete square, which means that this is some vector transpose q times that vector. Okay? As, for example, in our high school math, if we have x squared minus x, what number do you add to make that a complete square? Plus 1/4. So that you have x minus 1/2 squared, right? So we do the same thing. So this is their trick, very important trick. So now only for quadratics. Okay. Quadratic functions, where the function f is now 1/2 x transpose qx minus b transpose x, but we define v of x. Okay? And v of x is what? V of x equals f of x plus 1/2 x star transpose q x star, where x star is the global minimize of this quadratic optimization problem. Okay? Then what happens? You can easily show that v of x is simply a quadratic form. Okay? Be careful. This is a quadratic function. Now this is a quadratic form. Okay? It's, as I just told you, it's similar to what you do this. Okay? F of x equals x squared minus x. V of x is x squared minus x plus 1/4, so that you have x minus 1/2 squared. Got it? Okay. And as you see, I repeatedly do this simplification. Okay. Anyway, if this will work for every f from Rn to R, it must work for f from R1. Okay. That's why we do this. Okay. So whenever you see in the theorem or proposition of this chapter 8, is it chapter 8? Yeah. You say that, okay, this is for quadratics only. Okay, especially for this shifted one, upward or downward. Okay. It doesn't matter, right? Anyway, you need to subtract or subtract this number to have your minimum value, but your location of local minimum does not change, as you see here. Now, let me go back to our lecture note. Okay. So as you see, we have this v of x, okay, that involves this cube, so it's a quadratic form. Now, we first want to analyze the performance of our what? Steepest descent gradient method. So, what do we need to find? Alpha sub k, okay? For what? Not for general objective function, but for this quadratic function. Now, is it difficult? No, actually it's a piece of cake. Okay? So, as I just announced, not just 1 hour ago, announced, you will see additional problems to homework 2. The first one is that you find that the optimal step size is this. Okay? Not difficult. Okay? Actually, the textbook has it. So what I ask you to is that read the text and copy it at least once, carefully, so that you have that as your own. Got it? It's not that difficult. It's a piece of cake. But see that it's what? The step size, right? The step size, the optimal step size of your steepest descent gradient at the kth iteration depends on what? Of course, this Q matrix, because we only consider that quadratic function with this some positive definite Q function. By the way, we assume Q is positive definite. So it's invertible. Okay. So We assume Q is positive definite, so it's invertible, having all positive eigenvalues. Okay, so if our steepest descent gradient, let me repeat it to emphasize grade, algorithm applied to the quadratic form, we have this. This is now the steepest descent algorithm. Got it? You see? G, 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 G. What are they? Gradient of f at xk. Got it? So now we have derived the steepest descent gradient for the quadratics. Now let's analyze its performance. So let me, actually we need one more step. Okay? So this is for quadratics. And now, if I were you, I would say that, okay, let me be careful, just a second. Okay. Okay, from here, this bullet in page 5, okay, you see, lemma 8.1. From here to, let me see, yeah, from here to here, okay, in page 6, okay. This theorem 8.1, now you should be careful, is for general gradient methods. Okay, general. But for quadratics. Okay. It's not for just for steepest descent. Okay, steepest descent may also apply to this. Okay. What did I just say? 8.1 is for general gradient algorithm applied to solve a quadratic optimization problem. Okay, still quadratic, still quadratic. Okay, you write it here. Okay, still quadratic functions, but gradient method. Okay, so if you want, you may draw that Venn diagram, and you have 3 circles intersecting, and you may say that you shade this entire second circle and say that this is applicable for these algorithms. What does that mean? This will be used not only to analyze the performance of our steepest descent gradient, but fixed step size gradient method. As I told you, we will analyze mostly 2 algorithms, right? So this theorem is applicable to both of them, not just for steepest descent gradient, but for general gradient algorithm, but applied to quadratic optimization. Okay. You may say that, okay, I understand, but if I did not do this, probably you suffered a lot of confusion. Okay. Anyway, so this is very interesting result, and let's see the trick. Okay. So we've just decided to use v of x, not f of x, for convenience. Now, will it be true? Is it okay? Okay, so it starts with a claim. Okay, we have, see that? The function v, you can view it as f, but what is important with v? V is a quadratic form. Okay, v evaluated at case estimate. And now this is the function, objective function evaluated at k plus 1's estimate. Now, what does this mean? And also, it says that gamma sub k is always less than 1. Okay, you may say, oh, wait a minute. We only have fixed our search direction as negative gradient And for convenience, we just shifted our objective function so that we have a quadratic form as our objective function. Oh, is it really true? Now let's take a look at this. This trick gives us what? Always non-negative number wherever you evaluate this function. It's the difference between f. F may have negative value at many points, but this v is a complete square, so it is always non-negative, and it is 0 if and only if we have reached the global minimum. Okay? So you even say that, okay, it has iteration, so this is positive. Now, what about this? This may be non-negative, so just let me just say this is non-negative and this is non-negative. What is possible? 1 minus gamma sub k must be positive. Or if you say non-negative. What does that mean? Gamma sub k is less than or equal to 1, or in many cases, less than 1. Got it? And the second homework is now stated. Show this is true. And you may say that, wow, so complicated. Actually, it is not. It looks complicated, but it's just tedious substitution. Okay? It's not more than your calculus, actually. Just you substitute. Okay? And you can do it. So I have just added the second additional homework problem to your homework 2. Okay? You show this. Okay? And you may say that, it seems that depending on my choice of alpha sub k, gamma sub k may be greater than 1. No. Okay? No, never. Okay? If you have this as your objective function. Okay. So the authors kindly says that, hey, not difficult, substitution and tedious manipulations. Okay. Okay, next. This is very interesting. So they make some remarks. Okay, let me repeat. This theorem, lemma 8.1 is applicable to every gradient, whether step size is fixed or variable. Okay, every gradient algorithm, but applied to quadratics. Never forget. Okay. Anyway, it involves q, right? Where does that q comes? Quadratic function. Okay. Now, as I told you, gamma sub k is less than or equal to 1 always. Okay. Gamma sub k equals 1 implies you have reached the global minima of this quadratic form. Okay. Yeah. Now we have a theorem. Okay. Oh, okay. It seems that I have to give you the third additional problem. Okay. So from here, okay, from here till the next page. Okay. Yeah. It's about this theorem. Okay. So this lemma 8. So from here, okay, so lemma 8.1 and theorem 8.21 are related, okay? And for general gradient method applied to quadratics. Okay. Now, again we use V instead of F. And this is very, very interesting. Okay. This theorem says that suppose gamma sub k is positive for all k. Okay, what does that mean? Okay. So we little bit restrict. Okay, we little bit restrict our gradient method. So actually, not for every gradient method, but for some gradient methods, whether step size is variable or fixed. So suppose the gamma sub k is positive. as I just told you, gamma sub k is less than or equal to 1 always, but it may be negative because a negative number is okay. See that? If this value is minus 5, what does that mean? You violate the descent property, but it's okay. Right? So here, that theorem somehow what? Restricts little bit. Okay. This is greater than 0 and less than or equal to 1. What does that mean? You have descent property, actually. Right? Now, suppose gamma sub k is greater than, okay, so we have another restriction, okay, greater than 0 for all k. Then, this is surprising. This sequence of x converges to our global minimum, that is unique local minimum. Whether what is chosen as your initial guess. Okay? If and only if this gamma sub k's, when they are summed, blows up, tends to infinity. Okay? So this actually, if it is true, it simplifies our analysis a lot. For example, you choose a fixed step size, alpha, and show that first you derive gamma sub k. Gamma sub k may not be a constant, be careful. Even though you choose alpha sub k as alpha sub k as alpha, due to these gradients may differ at each step, gamma sub k may vary as a function of k. But anyway, somehow you show that their sum blows up. Then what does that mean? Your algorithm achieves global minimum. Very good. Whether it's fixed step size or not. And we will show also that the steepest descent gradient also satisfies this condition, so that it goes to global minimum. When what? They are applied to a quadratic function. Okay? Well, of course, it cannot converge to global minimum in general case. Okay? Never forget. Now you prove this. Okay? So what you do is this. This is easy because see that the Vx of k equals 1 minus gamma k minus 1 Vx of k minus 1, right? You remember the relation between two at k step and k plus 1 step, right? Proportional coefficient is 1 minus gamma k. So you replace this one with x k minus 1, then what? As you did in your high school math, similar to the geometric series, you have this result, okay? Product of gamma sub I. So what you need to show is that actually if, okay, this is true if and only if this goes to 0, right? Because what? We have a quadratic, positive definite quadratic form. So this value is 0 means that we have reached our global minimum. Okay? So you want to show that this, if and only if this is 0. Okay? Got it? So it is globally convergent if and only if this is true, if and only if sum of gamma sub I is blow up. So what you need to show is this one just. And it requires positivity of gamma sub k, so it is previously assumed. Anyway, you prove that gamma sub I is less than 1 and greater than 0, then they are equal statements. So what you do is that you first prove if this is true, that is true. Okay, so you prove direct part. And you prove the converse. Done. Okay? For the proof, see the textbook. Okay, so you have 3 additional homework problems that will greatly help you. Okay, so let me stop here. We have progressed a lot today, and next week, next Monday, what we are going to see is this. Now we apply this general result for gradient algorithms applied to quadratics to analyze first the steepest descent algorithms behavior, global convergence when applied to quadratics. It's somehow obvious, right? Anyway, converge the optimum. The second is very interesting. Some fixed step size algorithms goes to the global minimum when it is applied to a quadratic function by using this general result. A little bit restricted, but anyway. Okay, so we will see two very interesting results. Okay, that's all for the day.